say a yes or a no. Okay, yes, great, thank you very much. Right, wrong one. Okay, so I'll just pull up my papers of the things that I plan to discuss this evening. Now, so we're here for Math7502. Welcome back, everyone. I hope you had a great break. I certainly had a nice rest. Got to go up north for a little bit, which was interesting. Okay, so we're continuing on to introduce the problems in your assignment 2. And that brings me to question 4, because we've already discussed questions 1, 2, and 3. Now, if you missed that, you can go back and look at the YouTube video of those sessions before the break. Okay, so anyway, continuing to introduce these, let's have a look at this question 4. So here we have, we're given a matrix S, and it has these entries in it. They're letters A and B. Oh, hang on, just give me a second. I thought something was wrong. So I'm going to project the desktop in the room as well to make that a little bit easier for those of you in the room with us. So hopefully that turns on and starts going. I was focusing on the Zoom session anyway, so sorry, guys. That'll be up and running. I can see it already. Okay, great. So here we have a matrix. It's a 3 by 3 matrix. It's got A's and B's in it. Okay, and we are asked to prove basically that if A and B are real numbers, then S has eigenvectors that are real. And then I'm going to list some steps for what you think about, right? So I really want to avoid doing any of this problem, right? Because it's your problem to do, right? And it's not fair of me to go ahead and do any of that. So I'm just going to talk about some steps for that. Okay, so the first step that you should consider, and hang on, I'll grab my working pen. Don't worry, Walla, I've got several. Thank you. You're quite attentive. Okay, so the steps of this. First, you want to find roots of a cubic polynomial, f of lambda, and that's going to be equal to the determinant of s minus lambda I, right? Remember, this is how you find eigenvalues. And so if you're going to prove that the eigenvectors are can be represented with real numbers, then you first need the eigenvalues, correct? So you calculate this determinant, that's a cubic polynomial in the letter lambda, and then you solve that equals 0. So solve for this equal to 0, and you should be able to find 3 values, right? I won't tell you what they are. You've got to do that. All right, so next, you want to show those as lambda 1, lambda 2, and lambda 3, right? Okay, once you've got that, okay, so in other words, for each lambda j, where j goes from 1, 2, and 3. Now these could be repeated, right? They could be repeated roots of this cubic. But for each eigenvalue, you want to row reduce that matrix. So S minus lambda j times I, right? Because what you're doing is you're finding an element of the null space of this matrix. So in other words, hang on. Okay, the screen's just gone black. And yeah, so this computer just reverted back to no image. So I'll press desktop again. If I don't see that, just let me know and I'll press it again. It'll be a little bit annoying. You may find it easier to log into Zoom, those of you in class. Up to you, but I'll try to keep this displaying what's going on here. Okay, so you're calculating the null space of S minus lambda j times I to get X subscript J, the eigen vectors. And I'm going to abbreviate these because I don't want to each time write out eigenvalue and eigenvector. All right, so now your question is, do all of these eigenvectors, do they have real entries? So do they have real entries, question? Or if they don't have real entries, can you scale it so that they do? Because remember, an eigenvector is a representative of several possible elements of that null space. Okay, so you can pull out factors and simplify it. So it could be something like square root of -1 being I, followed by I, followed by I. And then you can factor that I out and have 1, 1, 1, for example, right? So that has all real entries. Okay, next one. So the next question basically says, show that for any vector x, x1, x2, x3 transpose, x transpose s times x is given by this expression. All right, and it's a nice expression. Now, I'll note, so I've got the assignment here, so just pull it off. Okay, somehow I saw that differently, so I've got nothing to talk about with respect to that. That's the same as this. Okay, so all you have to do is expand x transpose s times x, where s is this matrix up here. Collect like terms. And then factorize. Okay, and then you should be able to obtain that expression. All right, so this is an easy one. All right, and you should even be able to do that by hand, right? You don't necessarily need a computer to do that. But it doesn't hurt to check, right? Okay, so let's move on to the next part. Now the next one says, use as many methods as you can to determine for which values of A, B, the matrix S is positive, semi-definite, and positive definite. All right, so we need definitions of these, and I can see the screen's just, oh no, it's back. But it's not back there. Okay, so I'll press desktop again. All right, so if we're using as many methods as we can, well, I don't think that's quite what was meant in that question. I think what the question means is use as many methods as you need to determine for which values of A and B the matrix S is positive, semi-definite, and positive definite. Okay, so we need a definition. Now at this point, I think I'm just going to show you, right? Because I've got some things already written here, and I think I need to leave enough time for a while. Okay, so I'm just going to pull up. I was going to write there, but I don't think I will now. Okay, so basically you have this. A square symmetric matrix is positive definite, and you can see I've abbreviated it there. If x transpose x times s is positive, remember that's a scalar, right? When you multiply it all out, or it's a matrix with one scalar in it, but you can think of it as a scalar. Okay, if this is positive for all column vectors, that's what I mean there, column vector, x not equal to 0. Okay, because remember if x is treated as a row vector, then you get something different, right? So it's a column vector, so it's got to be a non-zero, and the key word here is for all non-zero column vectors. Okay, so positive semi-definite if this is greater or equal to 0 for all column vectors, right? And you don't have to have this non-zero. So I've scribbled that out, accidentally having written that. Okay, now the hint to doing this question basically is, it's obvious, right? Because you've got part B just above that. So the hint is to use part B, right? You know that you've got this expression if you were able to prove that. And then the key phrase here is, in the definition, is the phrase for all, okay? So that's all the hint I'm going to give you for that one, because I think it's a very strong hint. Okay, moving on, let's have a look at 4D, which is a bit more involved. Now I've got right here to see my notes. So I'll go ahead and see my notes, and I'll just display this just in the same way, but let's read the question first. So we've got a function, and basically it's mapping triples to real numbers, triples of real numbers to real numbers. Now, in this case, that same S is the Hessian of F. All right? And I'll tell you what the Hessian is in a moment. But it's the Hessian at this point, x superscript 0. So some particular point. All right, it's gone black again, so I'll press desktop. All of that will happen to you too, most likely. So I'm just on this touch screen pressing desktop. Okay, so the question is, oh, sorry, we've got more facts here. So the gradient vector of f at x0 is the 0 vector, so that means that x is a critical point. What are the conditions on A and B for x superscript 0 to be a local min or max? All right, so again, I'm not going to show you how to do this. I'm just going to define a few things for you and then tell you some facts, right? And these are facts that you can readily find on Wikipedia, but you're really not meant to do that, right? You've got to find it in a book because anyone can change Wikipedia. But I did find a lot of useful things on Wikipedia. Okay, so here is our Hessian matrix, right? It's got second order partial derivatives in it, and they follow this nice pattern according to the position in the matrix. All right, and we're told that this Hessian matrix is the same as S. Okay, and now we know that by definition that the Jacobian of grad F at x0 is that Hessian matrix, right? So this is a relationship between the Jacobian and the Hessian. All right, so now, if this is the case that F has this Hessian right here, then here's an example of it, right? And it's just this quadratic form. So this ternary quadratic form, a over 2 x1 squared plus a times x1, x2, and so on, right? If you take second derivatives, put that in a Hessian matrix just like this, you'll get this, okay? So this is a fine example. It's not the only example, but it's a fine example to think about. All right, and I should probably zoom in a little bit on that if I can. All right, just so that people can pause that and have a look at it. All right, so now let's consider some facts. If the Hessian is positive definite at x0, x superscript 0, then F has a local min at x superscript 0. Okay, now you've got to think about this in the context of previous questions, right? Because a question before that asked you, is the matrix positive definite? Is it positive semi-definite? Okay. So, so maybe those definitions are relevant, maybe they're not, right? But it's something for you to think about. Okay, also, if the Hessian is negative definite, now negative definite is just like it seems, you turn the inequality around in the definition. Okay, and I'll press desktop again. All right, then we've got a local maximum at x superscript 0. All right, if the Hessian has both positive and negative eigenvalues, then you could consider the analog of the surface as a saddle. Okay, so if you're thinking about a function of two variables, so that would correspond to a 2 by 2 matrix, but if that matrix had a positive and a negative eigenvalue, then you'd be looking at a saddle, all right? So we call this, as a form, we call this form indefinite. Okay, great, so let's move on and talk about the rest of my notes. Oops, That's question 4D, which I got here. All right, now here's some things I suggest that you think about. Now you may find that they're not so relevant for your problem, but it's just some things for you to think about along the way. So this one says, use the expression for f on the previous page to calculate the gradient vector of f. So what I'm saying is take that ternary quadratic form that I showed you that has the Hessian that is s and calculate the gradient vector for it, okay? And then can you show that x superscript 0 belongs to the null space of s if and only if the gradient vector of f at x superscript 0 is the 0 vector. All right? So that's probably a useful thing to think about. Okay? Now, we've got a couple more definitions I want to show you before I go on to some other problems. So we have a twice differentiable real function f has a local minimum x superscript 0 if we have two conditions met. The gradient vector f at x superscript 0 is the 0 vector, and the Hessian matrix is positive semi-definite at x superscript 0. Okay, so you may find that useful. All right, so continuing. If S is a square symmetric matrix with entries that are real, then S is positive definite if and only if all of the eigenvalues are positive. Okay? And it's positive semi-definite if and only if all of the eigenvalues are greater or equal to 0. So that's another way to look at positive definite and positive semi-definite, other than the definition, right? So this would be a theorem that follows from that definition. All right, so I think you'll find all of those things useful to think about when it comes to doing question 4. All right, so that's all I have for discussing the assignment question 4, and I think I'll just turn it over to Walla now to make sure that we have enough time to discuss question 5, and then after that we'll come back and do some other problems on positive definite, positive semi-definite, negative definite, and so on. Okay, so I'll talk to you in a moment. Thanks, Walla.
Okay, now we will move to question 5. In question 5, they ask you, take a selfie of yourself and transfer it to 2,000 times 300 times 200 monochromes matrix with elements in the range 0 to 1. If you prefer a different picture, use the instead, but make sure that it is a picture that you like. You need to take a selfie for yourself, then you need to change the size to become 300 times 200. Because we need to make it as a matrix. And part A, they ask you, plot your selfie using heat map. We need to use heat map. This is from Julia. How we can plot your image using heat map. Here, there is some code may help you. Let me show you. You will discuss this next Monday with Dr. Yuni also. At the beginning, you need to use some packages. You need to use a package, the first one using image and image magic, these two packages. Then you need to load your image. So you put the name of your image. Here we use load because we need to upload your photo and the name of your image, and we need to be sure that we put it into quotation. And you be sure that you write the name is correctly. This is the first step. The second step, you need to define the matrix A. You can find more details about matrix A in Julia book, I think, section 1.13. Why we can build this matrix A. We can use different colors, red, green, and blue. Then we can directly use heat map. Okay, here, for example, this is heat map for baby. Just we use heat map for the matrix A, and we put that the region false and Y flip that. Okay, this is what you will do, the same thing, but in your image. This is in part A. Okay. In part B, they ask you, now present low rank SVD based approximation of your selfie.
You just press desktop.
Yeah. Yeah. In part B, they ask, now present low rank SVD based approximations of your selfie, including rank. We need to put different ranks, I think 6 or 7, 1, 5, 10, 15, 20, 40, 80, 160, and 200. The last one being full rank, because here the dimension 200, and we need to convert our image as a matrix with the 300 times 200, and 200 is a full rank. Use the Julia SVD function for this purpose. SVD means singular value decomposition. If we have a matrix A, in general, SVD means singular value decomposition. What that means, if we have a matrix A with the dimension m times n, we can write this matrix as U times sigma times V transpose, where is the dimension of U equal m times n, and the dimension of sigma is m is n times n. This matrix is a diagonal matrix. And V transpose, the dimension of this matrix is n times m. Okay, this is the meaning of SVD. We can decompose the matrix A and write it as U times sigma times V transpose. In general, the rank of matrix A depends on the rank of the matrix sigma. If we can define the matrix of the rank of the matrix sigma, we can know what the ranks of matrix A. Okay. In general, matrix U and V can be real number and can be complex number inside U and V. But for sigma, all the time it's real number and non-zero. All the entries is non-zero also and are real number. U and V transpose can be complex or real, but sigma all the time consists of a real number and non-zero. Okay, we call U left singular vector, and we call V as right singular vector, and sigma called it singular value. Here sigma is a singular value. We call it sigma singular value. Okay, we call U as left singular vector, and V transpose we call it right singular vector. Okay, so we need to find SVD. SVD is a package also. It's defined in Julia. Just you can put SVD directly and put the matrix A. For example, here. Okay. Here we can find the size of matrix A, or the size of matrix A. You need to change the size in your question to become 300 times 200. The number of rows is 300, and the number of columns is 200. And you need to find the rank of matrix. Now you need to change the rank. At the beginning, you need to try 1, then 5, then 10, then 15, then 20, then 40, then 50, until 200, okay? There is a function inside Julia called SVD. If you have a matrix A, you can directly find the value of SVD here. F equal here SVD of this matrix A. And if you try to find the value of U and the value of V and the value of sigma, and we said that U is left singular vectors and sigma is right singular vector and sigma is a diagonal, we find the value of U by multiplying this value of F. Yeah, multiply F with U. We need to find it. And to find the value of V, if we multiply F with U, and try to maximize, to find the maximum, the absolute value of the matrix A minus this decomposition, it will be a very small number, or it's similar, or it's approximately to 0. Okay, so just you need to use SVD and change the rank of the matrix A. This is what you need to do for part B. In part C, they ask you, determine what you believe is the optimal rank. Compute the storage saving with this rank approximation. How many numbers are needed in comparison to 200 times 300? You need to find optimal rank. You need to try these numbers. Here we have 6 numbers. You need to find which one is optimal. And to know which one is optimal, you need to calculate the storage saving in your computer, okay? Which has the lowest one is the optimal one. This is for part C. And you will know more about this question in your lecture next week. Okay, now you can continue with some fundamental.
Okay, so hello again. I'm just going to do a couple of problems with you, right? That hopefully clarifies the notion of positive definite and positive semi-definite. All right, so starting at the top, if A is symmetric, then all eigenvalues are real and eigenvectors are orthogonal. Okay, so that's an important fact about symmetric matrices. All right, so let's have a look at this first question. We've got a matrix, it's 2 by 2. We can see that it's symmetric. Is it positive definite? Is it positive semi-definite? Is it negative definite? Is it negative semi-definite? Or is it indefinite? Okay, so we've got several possibilities. So what we want to do here is take the eigenvalues, all right? So let's begin. So we'll calculate the determinant of A minus lambda I. Okay, and so that is the determinant of 1 minus lambda, 2, 2, and 1 minus lambda. Now taking this, so it's 1 minus lambda squared, but there are 2 of them there, so I can express that as lambda minus 1 squared, and then minus the 2 times 2, which is 4. Okay, so next we want to expand this and then factorize it. So expanding, we've got lambda squared minus 2 lambda plus 1 minus 4. So that's a minus 3 there, right? Minus 3. And now we can see that it factorizes fairly easily. And we've got lambda is a minus 1, lambda minus 3. So I've always got to write that and then change the signs to make it work. Okay, so I want this one to be positive. And now it multiplies out to give me that. Okay, so now I see that these, the 2 roots of this expression are minus 1 and 3. Okay, so lambda 1 is minus 1, lambda 2 is 3. So these are our eigenvalues. All right, now remember the theorem that said if the eigenvalues have different sign, then it's indefinite. Okay, so this is negative, this is positive, so A is indefinite. All right, so therefore it's not positive definite, it's not positive semi-definite, it's not negative definite, it's not negative semi-definite, it's indefinite. All right, so would it help if I calculated the corresponding quadratic form? Possibly, so let's go ahead and do that. So I want x, y multiplied by A, 1, 2, 2, 1, multiplied by x, y. Okay, so I'll just multiply this out. Now this product here, let's see, that'll be x plus 2y there. And then in the bottom, we'll have 2x plus a single y. And then here we still have the xy. Okay, now if I multiply this part out, I get x squared plus 2xy. We'll run out of paper here, so I'll just grab some more. Okay, so we've got x squared plus 2xy, and then in the bottom, all right, so the y times this one gives us plus 2xy plus y squared. Okay, and now, so if I simplify this, we've got x squared plus 4xy plus y squared. All right, so I believe that that should give you a saddle since this is indefinite, but you should probably go ahead and plot that. And hopefully I've calculated that correctly. I think I have. Yeah. All right, so I'm saying now plot the surface f of xy is x squared plus 4xy plus y squared. Is it a saddle? Right, if it's indefinite, then it should be. Okay, so let's move on and look at the next question we've got for you here. So now we've got b subscript s is now given by a plus s times I. And our question is, what is the least real number s such that b subscript s is positive definite? Okay, so what I want to do now is, again, take the eigenvalues, right? And so I can see what they are because now we'll have 1 plus s, and then 2, and then 2, and then 1 plus s, right? And if we now subtract lambda I, we have a minus lambda in there, and a minus lambda there, and now we take the determinant of this. All right, so this determinant is just the same as, and you can see that here because I've got, this is a lot like what I had up there. So it's basically just 1 plus s minus lambda squared minus 4. Okay, and I want to expand this. And then calculate the eigenvalues. Okay, so we have lambda minus s plus 1, and then lambda minus s minus 3 when we factorize that. And then, so now we see what the eigenvalues are in this case. So we've got lambda 1 is equal to s minus 1, and lambda 2 is equal to s plus 3. Okay, so our question now is, if this is positive definite, then we need these to be positive, right? Okay, so what is the s such that both of these are positive, or the least such s? All right, so we see from this that s has to be greater than 1 for this to work, right? And that makes this one work too. So s is greater than 1 So in other words, if S is greater than 1, then positive definite matrix. Okay, but in fact, there is no such least S, right? Because it's basically, it would have to be S plus epsilon, where epsilon is the smallest possible positive number, but in fact, there is no such, 1 plus S epsilon, but there's no such least number that is greater than 1, okay? So there's this is slightly problematic, that question, but we get the general idea, right? It's basically 1 plus epsilon, even though that's not any particular number. Okay? All right, so that's all I have to say about that. Wallace is going to come and talk about the rest of the problems that will be helpful for you. So thanks, Walla.
Yeah. We need to prove a question here. They ask you, show that the quadratic form X transpose AX can be written as X transpose AX equal the summation I from I equal 1 . Yeah, we need to write X transpose AX as the summation from I equal 1 to n, summation from I equal 1 to n, Aij xi multiply with xj. Let's start with write the product of A transpose A times x, this part. If we try to write the multiplication between A times x, here we have the matrix A, which is a square matrix, multiply with x, which is a vector. This will give you the inner part, which equal the summation from j equal 1 to n for Aij times xj. Let's try to expand. This is equal A1j xj plus A, yeah, this is the first, sorry. This is equal A1j xj, the first one, summation of A2j xj up to summation of A_nj times xj. This is the vector. Okay, if you try to multiply A, the matrix A, with different entries, times the vector x, this will give you the summation from, because here we have the remaining from I equal 1 to n, so I keep it. This is equal summation from summation for A1j times xj up to ANJ times xj. But here we have X transpose AX. So we need to multiply this vector by X transpose. X transpose, the interest of X transpose is X transpose equal x1, x2 up to xn. If you try to multiply these together, so we need to multiply the first entry with the first entry here. So this will give you the summation from I equal 1 to n, and the summation from j equal 1 to n for Aij xi xj. Okay, just you need to expand at the beginning the multiplication between A and X, and then multiply the answer by X transpose. This is for this one. Okay. Is it clear for you? Yeah. For the second one, they ask, prove that if a diagonal entry in A is negative, then it isn't positive definite. If we have a matrix A, this matrix A is a diagonal matrix, and the entry of this matrix all are negative. We need to show that this matrix will not be a positive definite. For example, if you have a matrix A equal, here we have minus A11, here 0, 0. Here we have 0, minus A2, 2, 0, 0, minus here 0 because it's diagonal matrix minus A3, etc. For example, it says 3 by 3 matrix. This matrix, all the entries in the diagonal are negative. Okay, this is the matrix A. Suppose that we have X, which is a vector, and X not equal to 0. If you choose that X to be E3, for example, because you have 3 times E3. So if you have a matrix A with II, because here this is 1, 1, so II we can put it, 2, 2, we can put it II, all the time is negative, and we choose the vector X to become EI. EI means, here we have E3, means this is equal 0, 0, and 1. Okay, if you try to find X transpose times A times X, what will the answer? If you try to multiply, here we have a 3 times 3 matrix. If you try to substitute, here we have X transpose, which equal E3 times the matrix A times the vector X. This is all the time will give you the matrix A. And the matrix A has the diagonal all the time is negative. This is will give you A, I. And LII all the time is negative. So this is negative. So this matrix will not be a positive definite. So this matrix will be not a positive definite. Because if you suppose that X be a vector, a unit vector, this is will give you all the time the same matrix, and this matrix, which the diagonal of this matrix all the time is negative. So the answer all the time is negative. Is it clear for you? Okay. Last one. They ask, prove that a sum of 2 positive definite matrices is a positive definite. If we have 2 matrices, matrix A and matrix B, matrix A is a positive definite and matrix B is a positive definite. They ask you how you need to prove that the sum of these 2 matrices also is a positive definite. How we can prove that? At the beginning, suppose that we have 2 matrices, A and B, both are positive definite. Let A and B be a positive definite matrix. Be a positive definite matrix. What's the meaning of positive definite matrices? That means X transpose A times X greater than 0 and X transpose B times X also greater than 0. If you try to add these together, if we needed to add X transpose AX plus X transpose B times X, because this one is positive and this one is positive, the sum of positive plus positive all the time is positive. So this is all the time is positive. Now we need to use the distribution law. Now let's try to use distribution law. Let's try to use distributive law. Of matrix multiplication. So here we have X transpose AX plus X transpose BX. We can write it as X transpose. Here we can write A plus B, and all of these multiply with X. And we said before that X transpose AX times plus X transpose times B times X, it's positive. So the answer here also is positive because this part is positive. So this part also is positive. So this part also is positive. So the summation of A plus B is also a positive definite. This is the proof for this question. So if you have two matrices, both are positive definite, the summation of these two matrices all the time is positive definite. Yeah. Is there any question? Yeah.
Okay, so we're done for now. We'll start again.
Yeah.
Thanks, everyone. We're starting again at 6. Okay, sure. And can we go sit down? Yeah. Notes on it. So just wait for me to grab the notes on that. Okay, which one? Let's see. Okay, so basically derive an expression for the diagonal elements of H double Y, where that's A transpose A inverse times A transpose. Okay? You're not able to derive? Okay, so my hints on that were basically this, right? So let the inverse of this be. And then we'll go to that way. Let's check what we get. A big matrix with lots of small elements. Is that? Yeah, it looks like it. Yep, okay, then so you're looking at the diagonal elements, right? I guess you're seeking a pattern in that. Is that correct? Okay, so yep, sure. So you've got the, so you want to calculate the determinant of that two with the matrix. Yeah, no, that's right. Then hang on, what's the last entry? Oh, the inverse. Yeah. Cool. Okay. Yeah. Sure. Yeah. Sure. All right, so look up in here because I'll show you what I have. Right? I've got everything the same as what you have. So subbing is into this formula, right? I take the denominator over to the left-hand side just to make it simpler, and then basically subbing the numerators. We got this expression. So and all added together since the numerators are the same. So it makes two of those, or actually two of these. Well, they all have the same denominator, right? Yeah. But the numerator is the same as well. So you end up with all right, and then I don't know what the formula is to find it for whatever reason. So that's the formula there. Okay. Well, hang on. Maybe I can factorize. No. Remember, this is a vector here. Right? So we'll take this expression and scan that numerator and see what we have, right? And compare it with this. Make sure you're able to. Yeah, Q and R should be the same, right? Yes. Yeah. All right, so you add the two of those together and you get minus 2 of that. Now, I would take this numerator and expand it. The numerator in that expression. Expand it and see what you have compared to this. Yeah, I don't know. That looks like this. I don't know what the one is. Anyway, so you can photo that is. It's like we wrote the down that. But I would take what you have there and expand that square because that's a. Okay, you better hurry. We got 4 minutes. Well, the power should be the same as the 3. I mean, the sign. Okay, so if it's 4 by 4, then sure, power of 4 will be. But I think you were asked to do this in general, right? Oh, in part C, do that general. Minus each. Yeah. You, sure.
Yeah, and then I just do
Mhm. Yep. Well, it's, you put in a 4 by 4 matrix. It's fine.
I assume that I will not get powerful because it's not
Well, no, you put in a power. You put in a 4 by 4 matrix. Of course you get power. Are you doing B though?
Yeah.
Okay, then you need to enter the correct matrix. So it'll be a 3 by 3 matrix. Yeah. Well, yeah, but it takes this pattern, you see. So the top 2 rows would stop before the dot. So you have 0, 1, 0, 0, 0, 1, and then you have numbers. Yeah. Numbers. Yeah. I mean, I pretty much showed you guys what it was in that next session. So if you go back and look at the video of the session, right place, you see almost exactly the correct matrix. Right?
So it has to be a 3 by 3 matrix here.
That's right. For that particular one. But then later you've got to do it generally. Okay. All right. I better go and come up to the front end. Great. Hello. Only me again. Is that only me? Only you again, but there might be somebody on Zoom. Okay. You've left some paper here, voila. Now, do you mind if I just after that I go ahead and do the 2 questions?
Yeah.
So then it's easy. Then I can put my feet up after that, right?
Yeah.
Thanks. Okay, welcome back, everyone. Well, okay, so there's no one in here in the chat room yet, but there may come someone. We've got someone in the class, though, in case you are listening to the recording. Yeah.
Actually, I can see that.
Well, it depends. I mean, we're happy to help you.
That's fine.
Yeah.
I think that's,
Well, we'll hang out here for a few more minutes and see if someone wants to come in, and other than just you. But of course, we're here for you, right? Yeah.
I didn't get the picture.
Okay. Yeah. So look, we'll wait. Okay. So we've got Jonathan in here. So yeah, that's fine. So we'll go ahead and do it. Hi, Jonathan. Can you hear me?
I can hear you. Can you hear me?
All right. So, Jonathan, just give me a yes. Yeah, you can hear me. Okay. You don't think the volume is working? All right. I'll investigate that. Yeah, the screen is off. I wonder if the connections are maybe bad here. I'll have a feel around behind the dot cam. It seems to be disconnecting periodically. All right, and we'll just check on the volume as well in Zoom.
Sam, can you hear me?
Sorry, did you say something, Jonathan?
Yeah, I was just seeing if you could hear me.
Okay, so it seems like our speakers are on, but they're not very loud.
Oh, okay.
So anyway, I can't see any volume controls here. So I'll just have to go ahead. Can you hear me loudly enough, Jonathan, that I can continue? Yes, okay, great. All right, so since it's a bit soft when you say something because the speakers in this room are not very loud at the moment, maybe I'll get you to just type something in the chat and then you can speak because I'll be listening very carefully. Does that sound okay? Okay, good. All right, great. So now we're going to talk about question 4 and 5 this evening. So here's question 4, but I think I like the way it looks better when I've written it out by hand because it's a little bit bigger and a little less congested, possibly. You might feel differently. Anyway, and I don't think I'll do much writing at the moment. I'll just try to go slow with going over this. All right, so we've got a matrix S in this question, and it looks like this. It's got A's and B's in it. And so we're asked to, what happened to the camera? Why is the camera off suddenly? Was it on when you were talking? Jonathan, can you see my face? You can, okay, that's weird because I don't see it here on the, anyway, it doesn't matter. It doesn't matter. I don't need to see my face. I've seen it. All right. Sure. All right, so we've got to prove that if A and B are real numbers, then S has eigenvectors that have real entries. Okay, now keep in mind you can scale an eigenvector, right? So it could, for example, be I, and I, where I is the square root of -1. But this can be scaled back to be a real eigenvector because we can factor out the I and have 1, 1, 1, right? Okay, so, and what I'm going to do here is just give you a few hints or things to think about along the way because I really want to avoid doing this question because I've probably done too many questions in too much detail for you because, you know, it's an assignment. So anyway, so the first question, find roots of the polynomial f of lambda, which is the determinant of s minus lambda times I. All right, and express that in terms of a, b. So this will be a cubic polynomial here, right? Giving the eigenvalues, the roots are the eigenvalues of this polynomial. So once you've got that, your next step should be to basically label them lambda 1, lambda 2, lambda 3 for those things that you get as the roots, right? Okay, so because you need to correspond those to particular eigenvectors. So once you've got those, and you'll be able to express those in terms of A and B. Next, what you want to do is for each of the lambda j that you obtain, and so that'll be for j equals 1, 2, and 3, row reduce s minus lambda j times I. Okay, and the reason why you do that is you want to get a simple eigenvector. And remember, these eigenvectors belong to the null space of s minus lambda j times I. Okay, because what you're looking at is solving, wrong pen again. I have good pens and bad pens, and the bad pens look like the good pens because I buy the same brand and then pop the bad ones back into my pen holder. Anyway, so lambda j I and then times x j equals the 0 vector, right? So you're looking at this equation, which is why you want your eigenvectors in the null space, right? So to get elements of the null space, you row reduce this, so you get a very simple looking matrix, and then you can just more or less read off what the eigenvector is that corresponds to that eigenvalue. Okay, so this is corresponding to the null space. Xj belongs to the null space of S minus lambda Ji. Okay, great. So we've said that. Now your question to answer this, do all of the Xj that you get, remember you have 3 of them, do they have real entries? And if they don't have real entries, can they be scaled so that they do have real entries? Okay, good. Any questions about that, guys? No? Okay, I can see you nodding your head. All right, next one says, show that for any vector x equal to x1, x2, x3, and it's transposed, so this is a column vector, show that x transpose s times x is a times this sum squared plus b times this sum squared. All right, so your hints on doing that. Now, it's a very easy exercise, so I don't want to say much about it, right? But what you really want to do is just plain expand this out. You might start with expanding out s times x and then multiplying x transpose times the result, right? Expand that out, collect like terms, and then factorize. Okay, so you should be able to get this, even doing it by hand. Okay, let's move on to my next page. Now the next question here of 4 says, use as many methods as you can to determine for which values A and B the matrix S is positive, semi-definite, and positive definite, right? Because those have different definitions. So what I want to do for you here is just, now that's the same thing there, but I want to give you the definitions, right? So our first one is that a square symmetric matrix S is positive definite, and you can see that I've abbreviated that, if X transpose S times X is positive for all column vectors that are non-zero, and that's X. Okay, and furthermore, it's positive semi-definite if X transpose S times X is greater or equal to 0 for all column vectors X. Now, I previously accidentally wrote not equal to 0 there, so I've crossed it out because you don't need that in the definition. All right, so the hint is probably a bit obvious here too, because you've just done part B, and so you might think that part B is helpful, right? And it turns out that it is helpful. So basically what you want to do here is use this, and then notice that your key phrase, and this is my hint to you, your key phrase is the phrase for all in this definition, all right? So think about that when you do it. Okay, any questions, Jonathan, or anyone else? No? Okay, great.
And can you hear me?
Yeah, I can.
Going back to question part A, you said scaling a complex number to be real. Can you explain what you mean by that?
That was a little vague. So let's talk about that. So what I mean is, suppose you had x1 is equal to, say, I plus 1, 2i plus 2, and minus 5i plus 5, okay? So you can see that I can factorize out the I plus 1 out of them. And so I would have 1, 2, and minus 5. All right, so basically the point is that an element of the null space is not unique, right? So I could have this in my null space of the matrix I was looking at, but when I represent the eigenvector, I want to represent it with the simplest one. So I want to factor it out and say that the eigenvector is 1, 2, minus 5. Okay, you see this one here has complex values in it, right? But the one I want to use to represent the eigenvector is this one right here with only real entries in it, right? And so if we look at the question, it basically says, prove that the eigenvectors of S are real valued, and then in brackets it says not complex, right? But keep in mind that the real numbers is a subset, proper subset of the complex numbers, okay? So I think what he means there is they have no imaginary parts in them, right? You understand that, I'm sure. Okay, does that answer your question, Jonathan?
Yes, thank you.
Yeah, okay, great, good. Okay, so moving on to part G, which is a little bit more involved. All right, so I've rewritten it here, so let's just look at the way I've rewritten it, and I'll even keep this type above if you like to look at the type. Okay, so basically now you've got a function, f mapping triples of real numbers to real numbers, and you're told that S is the Hessian of F. Okay, and what the Hessian is just this matrix right here with second order partial derivatives in it. Okay, but it's the Hessian at x superscript 0. You're also told that the gradient vector of F at x superscript 0 is the 0 vector. So what this means is that x superscript 0 is a critical point. If you like to think of, you know, functions of one variable, for example, to make good analogies for what's going on. So a critical point would be something like the point 0, 0 of the cubic, or the point 0, 0 of the quadratic x squared, or some other critical point, right? Turning point. Okay, so what are the conditions on AB for x superscript 0, and in this case, since it's a triple, it'll be x1 superscript 0, x2 superscript 0, and so on. Okay, but what are the conditions on this to be a local max or a local minimum? Right, so here we've got the definition of the Hessian, and also we know that the Hessian is the Jacobian matrix of the gradient vector. In this case, we're talking about at x superscript 0, right? But what we're told here is that this Hessian is this, okay? So just to give you an example of a function f that has this particular Hessian, I've calculated one for you, but it's just an example, right? There are multiple that have this as a Hessian. I mean, just add some constant and you'll find another one to this, right? Okay, but this is a nice example to think of because it sort of makes it real for you, right? Or more tangible, I guess I should say. Okay, so this one here has this Hessian. Now what I want to do is just tell you a few definitions and say theorems, all right? So first thing we have is if a Hessian is positive definite at x superscript 0, then f has a local minimum at x superscript 0. All right, now have we defined that already? I think we did in the earlier questions, right? Yeah, I'm pretty sure I did, but let me know if I didn't. Okay, so it's if the Hessian is negative definite at x superscript 0, then f has a local max at x superscript 0. All right, but the key word here in these is positive definite, like certainly positive definite or certainly negative definite, as in no semi in there. Okay, and also if the Hessian has both positive and negative eigenvalues, the three-dimensional analog of this would be a saddle, right? And so if it doesn't have any of the above, then you've got an inconclusive case in classifying your matrix and the corresponding quadratic form. Okay, but another word, like the generalization of saddle, would be indefinite. So indefinite. Okay, So moving on to the next page. So what I want to suggest that you think about, so these are just things to think about. You may not find them useful, but I just found them interesting. So let's just discuss this. All right, so first, you might use the expression for f on the previous page to calculate the gradient vector of that f. And then you could show that x superscript 0 belongs to the null space of the matrix S if and only if the gradient vector at x superscript 0 is the 0 vector. All right? So that's just an interesting point. You might find it useful, you might not. Okay, but consider that, and I suggest you try it. All right, so now there were a couple of things I found on Wikipedia that were interesting and useful. Okay, now it's smart to go find them in a book rather than to find them in Wikipedia, because someone can change Wikipedia and it may not be accurate. Okay, but what I saw looked accurate. Okay, so a twice differentiable real function f has a local minimum x superscript 0 if you have two things satisfied. The gradient vector and of f at x superscript 0 is the 0 vector, and the Hessian matrix is positive semi-definite. Okay, so notice the difference here. I've given you a way to classify if you have positive definite and if you have positive semi-definite. All right, plus this one. So maybe you'll find that useful. All right, I can see GU saying something. Sam, is there no voice? GU, can you not hear me? And I think, well, no, I was speculating. I was speculating that was possibly because the desktop comes in and out of connection, but it's on now, so it's not that. So I'll see if I can turn up the.
GU can hear you now, he says. She says.
Yeah, you can hear me, great. So was that the same for you, Jonathan? Did I?
No, mine was good the whole time.
Okay, all right. So it might have just been your speaker volume there, hopefully, because that's fixable. All right, great. So good. And Jonathan, I've accidentally just learned how to turn your voice up, because all I have to do is press the program audio on this touch screen in the room, and you just got a lot louder. You want to try speaking again? Great.
Yeah. How's that? Yeah.
That's
okay.
excellent.
Cool.
I can hear you like you're in the room. Okay, great. So where were we? So we just talked about this point. Any questions about that? All right. So next, if S is a square symmetric matrix with entries that are real, then S is positive definite if and only if all the eigenvalues are positive. And it's positive semi-definite if and only if all of the eigenvalues are greater or equal to 0. And there's more to this, right? More to this theorem that follows from the definition. Because you can get negative semi-definite if the eigenvalues are all negative. Sorry, did I say semi-definite? I don't remember if I said semi-definite or definite. What I mean to say is negative definite if all the eigenvalues are negative, and negative semi-definite if all the eigenvalues are less than or equal to 0. Okay. All right, so moving on. Now we've got some questions, and I think I'll write these out by hand because they're fairly simple to write. I'll have a peek at the time. I think that leaves enough time for Walla because you finished early, Walla. Okay, so now I'm finished talking about that question 4 of the assignment. Walla will talk about question 5, but before she does come up and talk to you about question 5, I'm going to talk to you about some aspects of 2x2 positive definite matrices just to make it, I guess, more tangible for you. Okay, so we've got another result here. If S is a symmetric matrix, then all eigenvalues are real and all eigenvectors are orthogonal to one another. Okay, so that's an important point. Now, if we have, so this is a question, right, or a problem we'll do. If we have a 2 by 2 symmetric matrix, 1, 2, 2, 1, is this positive definite? Is it positive semi-definite? And so on, right? Meaning the other definitions. So what we should do here is calculate the eigenvalues, okay? And so actually, I think I'm just going to show you what I've got written out already because I've got some Julia code here too. And it's all neatly put together here. So, all right, so here's what we'll do. So first we take the determinant of A minus lambda I. Okay, so we put the A minus lambda I there, and now we're taking the determinant of this matrix, and we calculate that it's, well, it's 1 minus lambda times 1 minus lambda minus 2 times 2, right? But we can turn that around and write lambda minus 1 squared minus 4. And now what we want to do is expand that and factorize it so that we can find the eigenvalues. Okay, so we expand it, we get this, we find that that last term there is minus 3. And then we factorize that as lambda plus 1 and lambda minus 3. Okay, so now we see that minus 1 makes the 0 or 3 makes the 0. So these are zeros of this polynomial, otherwise called roots. So lambda 1 is minus 1 and lambda 2 is 3. So that's negative and positive respectively. Now it doesn't matter if you call lambda 1 to be 3 and lambda 2 is minus 1, right? Okay, but in Julia here, we've got this little Julia command. So in Julia, using linear algebra, and then we input A to be 1, 2, semicolon, 2, 1 for each of the rows of the matrix, and then just eigenvals round bracket A. And we should get minus 1 and 3 that agree with what we've done theoretically there. Okay, but what I've got here is the calculation X transpose times A times X. And so I've multiplied it out and started with this, and that's just X plus 2Y and 2X plus Y. So I'm calculating the corresponding quadratic form to the matrix A. All right, so we can see sort of what this might mean, that we've got two different signs of eigenvalues. Okay, so multiplying this out, then we get X squared plus X plus 2XY, and then plus 2XY again, and then plus Y squared. So in other words, we've got F of X and Y, X squared plus 4XY plus Y squared. And I think that this quadratic form here, when you plot this, it should give you a saddle, right? So you want to check that. Maybe I've made some mistake here. I don't think I did. But check that. It should be a saddle, right? Which would be the indefinite case. Okay, so yep, done that. Now, if we change this a little bit, right? So if we now have B subscript S is A plus S times I, what is the least S, being a real number, such that B subscript S is positive definite? Okay, so let's work through this and then let's have a look at that question again. So we just sub this in so here's our matrix A minus A plus S minus lambda I. Okay, and so we take the determinant of that, we have a polynomial. This one right here, we expand it, and then we can now see what the eigenvalues are. So we have S minus 1 and S plus 3. And since we ask for this to be positive definite, now we put on these inequalities and say this has to be positive and this has to be positive, and that is because of this point up here at the top. Okay, If A is symmetric, all of the eigenvalues are real. And, oh, sorry, I'm looking at the wrong thing. What I'm trying to say is positive definite. Never mind, forget that. Positive definite, okay? So positive definite, these two are positive. Okay, there are a lot of results there, aren't there? So what we need then is S to be greater than 1, because if S is greater than 1, then both of these inequalities are satisfied. Okay, but since that's a strict inequality and not S is greater or equal to 1, there's no least S, okay? So basically you just take that to be 1 plus epsilon satisfies this inequality, where epsilon is some infinitesimally small positive number. Okay, but there is no such least S. Okay, because there's no smallest number that is greater than 1. Okay, there's no such smallest number. All right, so that's all I have to say for tonight, and I'll just turn it over to Walla. Walla, I hope you have enough time, but it should be fine even if you don't. We've got the recording from the previous session. Thanks, guys. I'll talk to you later.
Hi, we will continue on question 5 in assignment 2. And question 5, they ask you, take a selfie of yourself and transform it to 300 times 200 monochrome matrix with elements in the range between 0 and 1. If you prefer a different picture, use that instead. But make sure that it is a picture that you took. You need to take a selfie for yourself, and you need to change the dimension for your selfie to become 300 times 200. Okay, so you need at the beginning to change the size. You can write numbers of rows equal 300 and numbers of columns equal 200. Then you can make your image 300 times 200. At the beginning, they ask you to plot your selfie using heat map. You need to use heat map in Julia. So to use heat map, you need to use some packages like image and like image magic. I will show you here an example, but you will talk about this next week in your lecture on Monday. But here there is an example. In this example, we have a baby picture. At the beginning, to use heat map, you need to install some packages. We need to install the package images and image magic. So we use these two packages. Then you need to load your photo. Be sure that you write this, the correct name and put it into quotation. So you call a function here image. So this is equal to your image. You need to load your image. Then we defined a matrix A. You can find more how to define this matrix in Julia book section 1.13. How to define this matrix. Then you can use heat map directly for this matrix A. Okay. To be sure about this image, you need to find the size of this matrix. To be sure that in our question to become, we needed it 300 times 200. So the answer here should be, in your case, 300 times 200. Then you can upload your photo and upload it using heat map. This is the first step you need to do. Is it clear for you? Okay. The second thing, now present low rank SVD based approximations of your selfie. Including rank, you need to use different rank for the matrix A, 1, 5, 10, 15, 20, 40, 80, 160, and 200. The last one being full rank. Why would here it's a full rank 200? Because our matrix is 300 times 200 and the numbers of columns is 200. Use the Julia SVD. We need to use SVD code function for this purpose. At the beginning, what the meaning of SVD? SVD means singular value decomposition. SVD means singular value decomposition. If you have a matrix A, you can write the matrix A as U times sigma times V transpose, and you will learn more about singular decomposition in your lecture. Here the matrix A with the dimension m times n. A is a matrix with m times n. U, the matrix with the dimension m times n also. Sigma with the dimension n times m. Sorry, m times n here. M times n here. M times, okay, n times m. And the vector V with the dimension n times n. This is V transpose, okay? We call that V left singular vector. We call V transpose right singular vector. And sigma, we call it diagonal, sigma, we call it singular value. This is singular value. This is, we call it left singular vector. And this is, we call it right singular vector. Vector U and V can be a complex or real number, but the matrix sigma all the time consists of real number. To know the rank of the matrix A, it's equal the same rank of the matrix sigma. So if you can find the rank of the matrix sigma, you can determine the rank of matrix A. In addition, this decomposition is not unique. So you can find different U, different sigma, and different V for the same matrix. All the time SVD is not unique. This is a brief about what is VD. In your question, what you need to do here, if we have a function f, we need to find SVD for the matrix A, which we built here. We found the value of matrix A. Yeah, we have this matrix. And try to find the value of SVD for this matrix, okay? In the part 2, you need to find SVD for matrix A with different rank. You need to try the matrix A on the rank 1, rank 5, rank 10, and you need to calculate SVD all the time for different ranks. This is the meaning of question 5, part B, to find SVD. Okay. In part C, they ask, determine what you believe is the optimal rank. Compute the storage saving with this rank approximation. How many numbers are needed in comparison to 200 times 300? You need to find an optimal rank. Here we try in part B, different ranks. You need to find which one is optimal rank. Optimal rank happens when you have a low storage in your computer, okay? Just we need to try many numbers and many ranks, and which will give you the smallest number is the optimal rank. Part C depends on part B. If you can find the value of SVD and try to calculate the storage saving, then you can define which one is optimal. This is for question 5 in assignment 2. And you will learn more about it in your lecture in next Monday. Okay.
Lala, can you say again what we mean by optimal?
By optimal means if we have many ranks, we have to try 1, 5, 10. We need to try many numbers to calculate SVD for the matrix A. The optimal one, which have the lowest storage in your computer. If you try to find the storage saving, with different rank, which will give you the smallest storage value. This is the optimal rank.
Okay, thanks.
Welcome. Now let's move to group some different questions. Here they ask, show that the quadratic form x transpose A times x can be written as x transpose A x. We can write it as a summation from I equal 1 to n, from j equal 1 to n, for the matrix Aij times xj times xa. We know that if we have x transpose Ax, we need to write this is in another formula. Let's try to write A times x. If we have a matrix A with interest A, which we call it matrix Aij, and we have x, which is a vector with different numbers, call it xj. So if you try to multiply Ax, we need to multiply here this matrix and with this vector. So we need to multiply each column by each row. If you try to multiply this, you will get, because we need to deal with also this part, if you try to multiply A times x, this will give you summation from j equal 1 to n for A1j times xj. The second one, summation from j equal 1 to n for A2j times xj, until summation from j equal 1 to n for anjxj. This is the first vector. If you multiply A times x. Now just we need to multiply both sides by x transpose. So we need to multiply here by x transpose and multiply here by x transpose. X transpose is a vector. The interest of this vector is x1, x2 up to x10. So we need to multiply this vector by this column. So at the beginning, we multiply x1 by this entry, x2 by the second entry, and added together. If you try to expand, this will give you the summation from I equal 1 to n, and the summation from j equal 1 to n for the matrix A times the vector I, the vector xi and xj. So we can write x transpose times A times x as the double summation of the matrix A times the vector xi times the vector xj. Okay. Let's move to another thing. Here they ask to prove that if a diagonal entry in matrix A is negative, then it is not positive definite. We know that the meaning of positive definite, that x transpose times A times x equal 0. This is the meaning of positive definite. In this equation, they said the matrix A is diagonal. This is the first thing. And the second thing, the interest of this matrix is negative. For example, if we have a matrix A, suppose it's that 3 by 3 matrix. Here we have a negative number, call it minus A11, 0, 0. There we have 0, minus A22, and here we have 0. Here we have 0, 0, and minus A33. This is a 3 by 3 matrix. And in the diagonal, all the numbers are negative. We can write the matrix A as the interest here, because just we have an interest in the diagonal, as AII, because here we have A11, A22, A33, up to ANN. And these numbers all the time are negative. So AII all the time are negative. This is given. Now we need to show that x transpose times A times x less than 0. Why? Because in the question they asked us to prove that it is not positive definite. We need to find the vector x, which is not equal to 0, and try to multiply x transpose times A times x and see what's happened. Suppose that we choose that the vector x equal EI. which is a unit vector. For example, here we have 3 times 3 matrix. We choose that x equal E3. And the vector E3 is equal 0, 0, and 1. Now let's try to substitute here and find x transpose times A times x. If you try to substitute and find the value of x transpose times A times x, well, this is equal. X transpose, we have the vector, the unit vector transpose. The unit vector means here EI, it's all the time equal 0, except at the number I equal 1. Here E3, it's equal 0 all the time, except in the third entry. Third entry here is 1. So we have EI transpose multiply with the matrix I, multiply with the vector EI. If you try to find this value, all the time will give you the matrix AI. And we said that the matrix AI is diagonal matrix, the first thing, and the second thing, it's negative. So AI all the time is negative. So we can show that this matrix all the time is not positive definite. So A is not positive definite. This is the proof for this question. Okay. Is there any question?
No.
Okay. Let's move to the last one. Okay. And the last question they ask, prove that the sum of two positive matrices is positive definite. If we have two matrices, for example, A and B, A is a positive definite, B is a positive definite, we need to show that if we add A plus B is a positive definite. So to prove this question, we need to suppose that we have two matrices, one A and B, and both are positive definite. So to prove this, we need to suppose that we have two matrices. Let A and B both positive definite matrices. Because we suppose it both are positive definite, that means X transpose A times X greater than 0. This is the first thing for the matrix A. And for the matrix B, X transpose B times X greater than 0. This one is positive and this one is positive. Let's try to add it up together. If we try to find the value of X transpose AX plus X transpose BX, here this is positive, plus positive all the time is positive. This is from linear algebra and from real number. If you have any real number, positive plus positive all the time give you positive, because this is positive plus positive will give you positive. This is the first thing. So these two values are positive. Now we need to use the distributive law if we need to multiply the matrix for matrix multiplication. Now, from the distributive law, of matrix multiplication, we have here X transpose AX plus X transpose BX. We can write it as X transpose multiply with A plus B times X. Okay, just we need to use distributive law. From this is law from multiplication. Here we can write X transpose AX plus X transpose BX as X transpose multiply with the summation between matrix A plus B times X. And we show here that this value all the time is positive. This part all the time is positive. And these two parts are equal. Because this part is positive, this part also should be positive. So X transpose times A plus B times X also is positive. So we can prove that A plus B also is a positive definite. is a positive definite. And this is the end of the book.
Hey, Walla.
Welcome.
Yeah, do you need the first half of that to prove that? Isn't the second half sufficient to prove that A plus B is positive?
Yeah, you can start from here. This is sufficient, but I need to show you that this part is positive. You can show just this part, and it's sufficient.
Yeah.
But I prefer to show you at the beginning that this is positive,
Yeah.
and this is positive, and the summation of two positive is positive.
Yeah. Okay,
Yeah.
great. Yeah, thanks.
You can just write this one, and it's enough.
Thanks, everyone.
Thanks, Walla. Okay, thanks, Jonathan. That's all for us for tonight. So
Thanks,
we'll see
Sam.
you
Thanks,
next
Walla.
time. Yep. Good
Sounds
night.
good. Cheers.
Thanks.